Ladies and gentlemen, please stand by. We'll be underway shortly. As a reminder, today's call is being recorded.
Hello, and welcome to today's webinar featuring Brian Scassellati. I'm Vincent Myers, a member of the Communications and Outreach team at SPARK, Simons Foundation Powering Autism Research for Knowledge, standing in for Claire Cameron. We'll begin today's discussion in a moment, but first, know that we'll be fielding questions at the end of today's presentation, but you can ask them at any point during the session. To ask a question, submit them via the chat window on your screen. And, as always, I'll note that if there are any members of the press tuning in, you can only report information presented during this webinar if that material has already been published elsewhere, or if you have first obtained express written permission from the presenter. Brian Scassellati joins us today from Yale University in Connecticut, where he is a professor of computer science, cognitive science, and mechanical engineering, and the director of the National Science Foundation Expedition on Socially Assistive Robotics. Prior to joining the faculty at Yale, Scassellati received his bachelor's and master's of engineering degrees from the Massachusetts Institute of Technology. He went on to study his PhD there in computer science under Rodney Brooks. Scassellati's research focuses on building embodied computational models of human social behavior, especially the developmental progression of early skills. Using computational modeling and socially interactive robots, his research evaluates models of how infants acquire social skills. He was named an Alfred P. Sloan Fellow and received an NSF Career Award in recognition of his work. Welcome, Professor Scassellati.
Well, thanks everyone for joining us. My name is Brian Scassellati, and I'm very happy to be with you all today. I want to tell you a little bit about this strange connection that we've seen over the last 15 years between robots and children and adults with autism spectrum disorder. And I'm going to try to keep this a little bit on the entertaining side, hopefully for all of you, because it is an interesting story. And so I'm going to go back 17 years to when I was first on the job market. I had been building large humanoid robots in graduate school, robots that were 6 foot tall and had an arm span of about 18 feet and weighed in the order of around 600 pounds. And I was looking for a job in computer science, and I had come to Yale to interview. And they had set up a wonderful schedule for me, and listed on that schedule were 2 people who, to me, looked like pediatricians, in part because I didn't know anything about the field. And I thought that it was a mistake, and I asked them whether or not this was, an error in someone's part. And they said, no, they've asked to speak with you. And so I went to the meeting, and that was the first time that I met Fred Volkmar and Ami Klin. And they asked me at the time, they said, could you bring one of your robots into our clinic? We've heard you've been building robots with social skills. And I told them that my robots were 600 pounds and that no, I wasn't going to trust them anywhere near children. And they asked me, they said, well, could you bring us any robot? And so I'm going to show you the very first robot that we brought into the clinic. And I don't show it whenever I talk to robotics audiences because it is so ridiculously simple that I get laughed out of the room. But here it is. This is a robot that we called Ezra. And Ezra was a very simple device that had 2 painted ping pong balls and a few spare scrap pieces of plastic and a hair tie for a mouth, and just a few servos to make it move around and engage with people socially. And the things that we saw during that very first meeting got all of us so excited that it's really spawned a very long collaboration that's involved more and more people over the years. And this is the kind of an effect that got so many people in robotics excited that we started to see people replicate these results with very different kinds of robots and in groups all over the world. And so let me first tell you a little bit about what happens every time we brought kids who are on the spectrum together with some kind of robotic technology. First of all, we saw a very high motivation in the children. And that's not really front page news. I gave a child a brand new robot toy and they were very excited. And that's to be expected. We also saw that they had a very sustained interest in the devices. They wanted to play with it, not just for 10 minutes or 20 minutes, but for 3 or 4 hours or for as long as we would let them go. Now, for many children who perseverate, especially with a new and interesting device, this again wasn't enough to get people excited. But what did really strike all of us is that for many of the children, we saw them behave with the robot with this increased level of social capability. They were doing things with the robot that they weren't typically using in their daily lives. They weren't doing this either with their parents or with their peers or with our clinicians. And that was what really got us all excited about this. Now, we've learned over the last 15 years quite a bit, but just to sort of anticipate a few questions, we know that this works with robots that are very different in terms of their physical form, whether it's something that's very humanoid or whether it is something animal-like, or whether it's something very robotic and abstract. Everything ranging from these sort of hybrid Barbie doll androids to things that look like dinosaurs or little snowmen, or even things that are completely without anthropomorphic characteristics, like this round ball. I think that there's a lot of interest in the kinds of device, but I want to focus mostly to start with today on the effect that we see. Now, when we started doing this work, most of the work was happening in these technology groups, and in these technology groups, we saw basically the worst kind of science that we could imagine because we were engineers, we were not scientists. We did things with very small sample sizes. We had no quantitative metrics, no control groups. We never talked about the diagnostic or the inclusionary criteria that we used. And we basically did what engineers do, which is we brought the device in, we saw that it worked, and we wrote up a result based on that. And while that was good enough for the engineering side of the world, for the clinical and the scientific side, this really wasn't satisfying. But the biggest mistake that we made, the one that is really the one that kind of haunts me to this day, is that we were extremely focused on the way that the individual would interact with the robot. That is, we were looking at the robot-directed behavior. And any good clinician would look at this situation and say, who cares? Why would you care about training someone to respond well to a robot? That's not giving them any capability that they don't already have. It's not helping them in their daily lives. So about 10 years ago, we recognized this error, and we started really trying to focus not just on what we could do in this robot-directed setting, but also what we could do to try to enhance human-to-human behavior and performance. And let me give you an example right from the beginning of what kinds of things we did and what we saw. And this is the first study, I think, that got many of those, that corrected many of those mistakes. This is a project that was done by Ellie Kim in my lab. And Ellie was interested in how we could introduce robots into a therapeutic setting. So we did the absolute simplest thing we could imagine, which is that we took a protocol that was being commonly used in the clinic here, and we took an applied behavioral analysis scenario in which we were working with adolescents who were having difficulty with vocal prosody, both recognition and expression. And we took those children, and one of the settings that they were using is that we had these practice games. And like any other ABA therapy, we were putting them in a scenario, asking them a question, and getting them to respond, and hopefully to respond using the appropriate intonation in their voice. So we took this standard clinical protocol, and we just replaced one of the people in this protocol with a robot. And we had to modify the protocol a little bit so that it could match the capabilities of the robot. And so here's what we did. We brought in this little dinosaur robot. It was a commercial product called Pleo that we had made arrangements with the company, so they gave us permission so that we could modify the robot. And we basically gutted the software of the robot and turned it into a system that we could control remotely that would do the things that we needed it to do for this therapy setting. And in this setting, the robot would walk across the little play mat that you see on the table there. And we told the child that the robot was afraid of water. And so while the robot walked across the table, whenever it got to one of the little painted rivers on the table, the robot would pause, and it would shake, and it would sound scared. And the child's job was to say something that sounded encouraging. Now, these were all children who were very verbal, and they all knew the right words to say, but they had difficulty in getting that intonation right. So I'm going to show you a video next of one child engaged in this scenario. He's a child we'd worked with at that point for many years, and I'm going to show you a little bit of his behavior before, during, and after the robot encounter. Now, the robot encounter lasted for only about 5 minutes, so it was a relatively short engagement. But I want you to look for two things in particular. I want you to look for, first of all, the difference in his behavior before and after the robot. And second, I want you to look for a particular behavior called social referencing. And that's that little glance that you do to make sure that something is okay. You look back at your parent or at your boss, and it's that little glance to just check in and say, oh, is that person frowning or smiling? That little tiny bit of information that you get from that social reference. That's a behavior that for this child, we rarely, if ever, saw him do that, either in the clinic or with his parents as they reported. And you're going to see him do it a couple of times in this video. So let's take a look at that. So here we go. I'll get my interface right. So this is his typical behavior beforehand.
Okay, so just sitting in a box somewhere.
Yeah.
What kind of games do you play?
What kind of games do I play with them? Like battles.
So notice that he doesn't make eye contact. He's not really engaged in the conversation. Then the robot comes out.
What are you stuck on?
I think he's okay.
You
coming up here, you're going to see a little of that social referencing right there. And you'll see him do it again shortly.
Think he's funny?
Yeah. Especially when he gets stuck.
Yeah.
And you hit it when you were doing something?
I don't remember. I must have banged it, or it just one day I tried to turn it on, it just wasn't working right.
Everything's fuzzy.
Yeah.
And did it have any sound when you turned it on?
So notice that there's a real difference in how engaged he is in this conversation before and after the robot. Before, he's not really making eye contact. He's not orienting towards us. Afterwards, the woman in brown at the far right is a therapist that he's seen for a number of years now. She's not unusual to him. She's not unknown to him. But afterwards, he's making eye contact and he's excited and engaged in the conversation. Notice that this is without the robot being present. That is, while the robot's there, he's very fixated on the robot. He's engaged and interested in the robot because it's new and novel and exciting. But after the robot's taken away, we see this increased in human-to-human social performance. And that was the thing that got us really excited. Now, we also saw these behaviors that were, in a way, very exciting for us to see. And in fact, on the left side of the screen, you can see what was a one-way mirror, and his parents were sitting behind that mirror. And they first offered to buy the robot, and then second wanted us to look away while they walked out of the room with the robot. But our question really was, is this just the novelty? Is this just the excitement of this new and brand new toy? And could we actually turn this excitement into something that really was therapeutic, that had some lasting value? So one immediate hypothesis that we came up with is that it is just the novelty, that it's that if we had done this with something else that was exciting and interesting, that we would have gotten the same kind of result. So our first question was to test exactly this. Is it just a novelty? So in the summer of, 2007, 2008, just before the first iPads and the first real tablets hit the market, we managed to get an early prototype tablet computer. And we introduced children in a three-part experiment to a block-building game that they played with an adult, then played with a robot, and then that we allowed them to play with just the tablet. And our idea of building this set of comparisons was that the interaction with the adult was going to be an inherently social task, but one that was not novel to the child. They'd had lots of experience by this point interacting with adults. The robot would be both social and novel, while the tablet would be novel but not at all social. So if it was just purely novelty that produced this effect, then we should see the same kind of thing happening with the tablet as we saw with the robot. Now, we followed a reasonable protocol, and we counterbalanced the order of these different conditions. We allowed for some time and play sessions in between so that we didn't see any fatigue effects. We brought in a sampling of about 24 kids, and we exposed them to all three protocols. And we looked at their behavior in each of these different scenarios. And to summarize it, I would say when they interacted with the adult, they were at best willing to take part in this engagement. It was not a terribly interesting task, and they definitely were not very interested in interacting with the adult. When they were interacting with the robot was exciting and new, and they were willing to play this relatively simple game with the robot. And when they had the tablet, they were very excited to play with the tablet, but not very excited to interact with anyone else. Now, I'll also point out and ask you to notice that in all the cases, we provided not only an interaction partner, like the person or the robot in the first two conditions, but in all three conditions, there was always someone else in the room. In this case, this is Ellie Kim, who's showing up in all three of these scenarios. Now, we looked first at just some simple measures of socialization and just asked simply, how often do we see these kids talking? How often do they do they speak in each of these three conditions? And sure enough, when the robot was around, the line in red in the middle there, they spoke more in the robot condition than they did in the adult condition or with the computer, with the tablet alone. Now, again, that could just be the novelty of the robot is really strong and really exciting. And so we divided this up and tried to break this down based on who the utterance was directed toward. And so if you look at utterances directed to the partner, so in the adult case directed to the adult, in the robot case directed to the robot, in the computer case directed to the tablet, we actually saw about the same amount of speech directed to the robot as there was to the adult partner. That is, we didn't see substantially more being directed just because they were excited about the robot. So where does that extra speech come from? Well, in fact, it comes from that third person in the room. And when the robot was present, we saw more speech directed at that third person, at, in this case, Ellie Kim, rather than when they were engaged in the adult condition or the computer condition. So if it had just been a novelty, we shouldn't have seen this change in direction. We shouldn't have seen this change just in the robot condition. We should have seen it in both the robot and the tablet condition. So it wasn't just the novelty of the device. There was something particular about this being both novel and social and engaged in that device. So in these two conditions, we were dealing with kids who were roughly 6 to 12 years old. I'm going to show you some work later that involves kids at different ages. But with these first two experiments, these were the sample of kids that we were most familiar with and working with. So if this isn't a novelty effect, what is it? And the thing I'm going to suggest is that this was really a technology problem, an AI problem, an artificial intelligence problem. And in fact, those kids who took part in the experiment with the dinosaur, while they had great responses to that particular device and to that particular setting, when we asked them to come back in the following days, we asked them to come back the day after their first exposure. And on the second day, we saw the same kind of results. We saw more orientation, we saw more relevant statements, more engagement, more eye contact, all sorts of good signs. Third day, we again saw really good engagement, same sort of effect. Fourth day, nothing. Fifth day, nothing. And the reason that we thought and focused in on the fact that this was a technology problem was that we were asking something that was really unreasonable of the children. We were asking them basically to laugh at the same joke over and over again. And as we all know, if I tell you the same joke every day for an entire week, by the fourth day, by the fifth day, it's just not funny anymore. We're asking them to engage in the same encounter, the same scripted experiment, the same exact protocol day after day. And that was because we had only programmed the robot to do one thing. And that this was not like what would be happening in therapy with a human therapist. This was not something that was going to be normal in any sense of the world. So we started looking at what it would take to be able to engage with the robot in a more rich way so that we could actually look at some kind of long-term interaction and start to ask the question, is this actually therapeutic? Or is this just something where it's a great experience, it's fun and engaging, but there's no value to it? So to do that, we had to be able to build robots that could customize their behavior, customize the content of what they were delivering, and the method in which it was being delivered to the particular needs of that child in the same way that a good teacher or a good coach would for anyone else. That is, we need to be able to build something that had more social complexity inside of itself. Okay. So over the last 5 to 7 years, we've been working on the underlying technologies that we need in order to build more robust long-term engagements. That means, first of all, we need to monitor and respond to more substantial and subtle social cues and model the dynamic of that social interaction. We need to be able to get the robot to personalize what it's doing to that particular child. And we need to have some kind of framework that's going to allow us to grow and change and direct the child towards some learning outcome, some desired learning outcome. So for the last 5 years, we've had this wonderful bit of funding from the National Science Foundation that's allowed us to do this in a staged way. We couldn't make this jump all at once. But over the 3 years, we've been looking to try to turn this from one step to another, to move from these short, controlled experiments in the clinic or in the laboratory to something that was more organic, more ongoing, more long-term, and deployed in the home in areas where we have sort of our best ability to engage with kids. Now, we haven't done this strictly with kids with ASD, and in fact, we have been working with a variety of robots that teach over the last 5 years. We've deployed robots that teach nutrition to first graders. And if you think there's a more challenging content than trying to get first graders to understand fiber or to want to learn about fiber, I challenge you to come up with that one because I couldn't. We've talked about language learning for kids in K through 2. We've done anti-bullying programs with robots for kids in 3rd grade. We're tutoring math for 5th and 6th graders. We've looked at adults. And we've even talked about doing language skills for 6 to 12-month-old deaf infants. And I'm going to show you some bits and pieces of this different work as I try to get to the question, which has really been, I've been struggling with for 15 years now, which is, why does this work? Why do we see kids respond to these devices in ways that they don't necessarily do with a clinician? Or with a parent. And I will preface this discussion by saying I've had probably 7 or 8 what I thought were good ideas about how this would be answered, and I've been wrong every time. So this is my 8th or 9th version of this, and I'm sure it's not completely true, but we keep getting a better and better answer each time. So for example, at first we thought it was maybe something to do with the fact that the robot was very predictable, that social responses from the robot were limited, and as such you could easily predict what was going to happen for a particular behavior, directed at the robot. It turns out that was not at all the case. If we gave kids, both typically developing kids and kids on the spectrum, from ages around 4 to around 10, an interaction with a completely predictable robot and a robot that was completely unpredictable, our typically developing kids showed a clear preference. Our kids with ASD showed no preference at all. So every time I've gone through this, I've come up with an answer. I thought this was it. This is the criteria. It has something to do with predictability or the simplicity of the visual stimulus or the approachability of the object. Every time I've gotten it wrong. But let me give you my best answer so far. But I think this is one of the things that is really the key question in this domain. Why does this work? So to get to my answer for right now, I'm going to introduce another little robot that we used to teach English language skills to kids who were in 1st and 2nd grade in a magnet school that dealt primarily with kids who were speaking Spanish or Portuguese at home and struggling to learn English in the public school system. And this is a little robot called Keep-On. It's a minimally anthropomorphic robot, and it's always good to see video. But this is a small 4 degree of freedom robot. It's about 5 inches tall from sort of the yellow part that you see. And it's a little bit expressive. You definitely get a sense of when it's looking at you, and it has some characteristics. Now, we brought this into into these first and second grade classrooms, and we initially asked the teachers there, what's the largest problem that you have? Most of them were public school teachers in a mid-sized city on the East Coast, and they all told us the same answer. They said, look, we've got a classroom of 25 kids, and we have no idea what the individual skills of any of the children are. Because every time we ask them a question or single them out, they've learned that they don't always say the answer in English in the correct way. And as a result, what they do is they deflect. They don't answer our question, and as such, we don't really know what they know and what they don't know. So we brought this robot in to do some one-on-one tutoring. And in this particular video, you're going to see one little boy, second grader, who's working with the robot, and the robot will tell him stories in Spanish, and his job is to translate parts of that into English. And as he does that, the robot is monitoring what he's doing, what he's saying, and then changing the story in the future so that it focuses on the skills that he needs the most help with. Now, in this particular clip, you're going to see him trying to translate the Spanish verb hacer, which in English you either translate as make or do. And this is one of the skills that kids have a particular difficulty with, because knowing whether it's make or do excuse me. Sorry about that, excuse my cough. Knowing whether it's make or do depends upon 14 different context rules. So in English, you would make your bed. You would never do your bed. But you do your homework. You wouldn't make your homework. And what you're going to see is you're going to see the robot ask him to make a translation, and you'll see him make a mistake. And that seems like an odd example to show you, but that's exactly the point. That with these robots, we sometimes get kids to do things that they're not really willing to do with a human instructor or in public. That is, it's not embarrassing to do it just with the robot. So here he is.
Necesito mi gorro extra. Por favor, también dile que haga espacio para mi gorro en inglés.
You can do a space more.
Bueno, estamos listos para irnos. Deberíamos de hacer un baile para celebrar todo nuestro trabajo duro. Dile a Spo en inglés que...
So instead of make more space, he says do a space more. He makes a mistake in front of the robot that we often wouldn't get him to make in any other context. And because he does that, we're able to train a model of which skills he knows and which skills he doesn't know. And using those models, we see some relatively dramatic learning performance. So these children had 5 sessions with the robot. Each session was about 15 to 20 minutes. And before those, the difference before they took those 5 sessions and after, on a standardized test that's typically given to this grade, this was not a test that we designed for this protocol ourselves, we saw changes from about a 30 to 40 percentile score up to about a 60 percentile score with the robot. And with the personalization that the robot could do, we saw improvement up to about 80 percentile. So these kids were able to find what they needed in this system. And the only reason that the system worked is that we were able to get them to make mistakes. That is, the robot was social enough for them to trigger social behavior and for them to learn from, but not too social. And that in particular is why I think that we maybe get some results with kids with ASD. Let me give you the corresponding version of this with a small twist that we're now doing with kids on the spectrum, which is that we are turning the tables a little bit and we're asking the children to be the experts and to teach the robot. So one of the great things about these robots is that in the same way that they don't trigger this social response, the robots don't have a particular social role. And so when we tell them, when we tell children that this robot needs help with the same skills that they've been learning, they're very willing to engage with the robot and they're very excited to do so. And so in this case, we've programmed this robot to make certain social mistakes, to interrupt frequently, to respond with very short responses, to look away while someone's talking, or to introduce an off-topic sentence. And when we do that, this is a great protocol for us to run because the kids engage very quickly with it, and they end up feeling like they have something to contribute here. They end up feeling like they have mastered those skills that they've worked so hard on. And that feeling of mastery is really critical. Now, to show you why we do this particularly with robots, I'm going to show you the same child engaged in the same task. On the bottom of the screen, you'll see him doing it with the robot head. And on the top of the screen, you'll see him doing it with one of our postdocs, Laura Boconfuso, who's right here. She's the woman on the far left. And you'll see the difference in how willing he is to engage in this same exercise, but with two different partners. So here he is. Again, this is the first minute or so of this exposure. On the bottom, he is already engaged with the robot. He actually was too excited to sit down initially. He started teaching the robot right away. On the top, he just doesn't engage with the task at all. And we've seen this with dozens of kids. This is a typical response. The idea that the adult is not the expert here is just really hard for them to grasp. But on the bottom, we've got a lot of focus. We're engaged in the task, and he's very adept at monitoring the robot's social cues, and he's having a nice time with it. So part of the reason that I now think that we actually get these interesting effects is that the robots are a very unique form of social stimulus. That is, they're social enough to trigger very instinctual social skills, very basic social skills. But they're not familiar enough that they provide the same sorts of associations that we have with more complex social criteria. So let me try to back that up for just a moment with another protocol that we've done with very young children, and looking at the way in which even infants will engage with these robotic systems. And I'll introduce quickly just a different domain that we've been working in, and that's working with infants who are 6 to 12 months old who are deaf. So we have a challenging domain here in that we see many kids who have either partial deafness, some hearing loss, or are completely deaf, who have very minimal exposure to language during the first year. Many of these children will go on to have cochlear implants or some other technologically based intervention, but this is an intervention that can't usually occur until 12 to 14 months of age. And so you have children, even when they have very well-meaning parents who are rapidly trying to learn to sign, who just can't keep up with the needs of the infant. We're not wired to learn language as an adult at nearly the rate that an infant can. So we started looking at whether we could provide a technology-based intervention here, but unfortunately most of our robots just can't sign. We know that we can build robots that even young infants will engage in. Andy Meltzoff has done some great work in this domain. But the robots don't have the manual dexterity or the physical expressiveness to really be able to provide good signed language input. Now, on the other side, we have things like virtual characters and avatars that do have the dexterity, that do have the expressiveness, at least to approach a reasonable stimulus. But we also have a lot of evidence from folks like Patricia Kuhl that children under the age of 2 don't really learn from screens. They'll stare at them, they'll be fascinated by them, but they won't actually learn directly from them. So our thought was to try to put these two things together that is to use both a robot and a virtual character as a social dyad, as a pair who would interact with each other and engage the infant with some very simple signs, the equivalent of nursery rhymes, simple phonetic structures. And just to give you an idea of what happens when we do this, I'm going to show you now a quick video. You're going to see two different views of the infant at the bottom, sitting on the parent's lap, and looking at the combined system of the robot and the virtual avatar. And in this system, one of the things you see is that the robot does certain behavior, like this very dramatic head nod that you can see it doing right now. And the avatar pays attention to the robot, and then the robot tries to direct attention to the avatar. The infant does some of the same things, like you just saw there. The infant does this dramatic head nod just a few seconds after the robot has done it. So we see even children as young as 6 and 7 months copying the simple behaviors of the robotic character. We also, though, then see the same things happening with the avatar. And in this case, I'll just skip right to the video so we don't waste too much time here. We see the infant learning this sign that involves the hand going up and down in a wave-like motion that the avatar on screen has been doing, and then replicating that sign. And I'm going to go back and show that one more time. Replicating that same sign while they're staring at the robot. That is, picking up a sign that they've seen from the character on the screen and trying to use it to engage that physical object. So we see both social learning, social engagement, and even transfer with very, very simple social behaviors with very, very young children. So we know that the robots will engage in this particular way. Let me now try to sort of get up to date here, and that I want to stop soon and answer some questions. We've also looked a little bit at how we can potentially use robots as diagnostic tools, because one of the wonderful things about these systems is that they are both quantitative and they are consistent across time. So we know that we put the robot in place, and whatever it does today is the same thing it's going to do tomorrow and the day after and the year after. And it's also going to do the same thing from child to child to child. So we've been working with a very simple robot, again, a commercial product called Sphero that we have changed and modified. And we have this little ball robot roll around on the floor. And we've programmed it to display different characterizations, sometimes acting like it's happy or sad or fearful. And let me give you a sampling of that. So here's the robot. When it is happy, it rolls around, it plays nice happy music, and it's hard to see in the video, but it flashes bright colors. And sometimes when the robot is angry, it rolls around and makes more dramatic, metallic sounding music, and it flashes red. And what's interesting is not what children do inherently with this robot, and in fact we see kids, both the typically developing child you're going to see on the top and the child who's later going to be diagnosed with ASD on the bottom, who both engage the robot. They follow it around, they chase it, they pick it up, they kick it, they lick it, they do everything you could imagine to this robot. But what's interesting is that they do it differently depending upon the state of the robot. That is, when the robot is, for example, in this angry mood, the child at the top will often stay farther away from it until it changes its expression, and then they'll go close again, whereas a child on the bottom will often go over and try to pick it up. And just from these simple diagnostics, we can even start to see statistically significant differences in the way the kids respond to that. For example, our kids with ASD will often go over to the sad robot, and they'll be very fascinated by it, but they'll almost never pick it up. They'll almost never direct that towards an adult, whereas our typically developing kids are. So we're looking at ways in which we can use the quantitative data from these systems to try to do early screening and diagnostics. But let me get back again to that very central question. Is this thing that we saw, this response that we saw early on with that dinosaur robot, is it just a mirage? Is it the kind of thing that's going to fade? Or can we actually use it to produce real change over a substantial period of time? So it's taken us about 10 years from when we started doing this to get the technology to the point where we were able to start testing this. And that's what we're engaged in doing right now. So right now we're in the middle of a very large deployment in which we are putting robots into 30 homes for a month each. And each of those robots is doing 30 minutes of social skills training with a child with autism every day for that month. And these robots, we go in and we bring in and install a touch screen and the robot and some recording equipment. And I drop it off on day 1 and I pick it up on day 30. And the robot engages with both the child and with one of the parents or caregivers. And they play different social skills games. And they focus on the same kinds of things that they'd be typically engaged in, and we've only selected kids where these are skills that they have difficulty with. They play games that involve understanding of appropriate emotion, directing joint attention, taking turns, and taking different perspectives. And the robot acts as a kind of moderator for these games. Most of the games are played with the child and the parent. Occasionally, the robot is one of the players in that game. The robot does things like it recognizes and responds to the individuals. It tracks where they're looking, what kinds of selections they're making on screen. It will sometimes, when, for example, we're talking about engaging with different emotional states, the robot will characterize them and display them. And most of the settings are designed so that it is a pairwise game between the child and the adult, with the robot acting as sort of the game moderator. Now, from a technology standpoint, we have to do this in what is perhaps the most complex environment known to robotics, which is a child's bedroom. It is an extremely complex visual domain, extremely complex auditory domain. There are a lot of things that make this really challenging, but we've gotten to the point where we're actually doing this now. We've finished 18 families. Each of the families we track for a 90-day period. They have the robot for a 30-day session in the middle of the time when we're tracking them. But we also do a social skills measurement with the child and with the family 30 days before the robot arrives, on the day the robot arrives, the day the robot leaves, and 30 days after the robot has left. So we're looking at both the kinds of growth that they're able to get over their standard period of time where there's no additional intervention, so what happens when the robot is there, and then what happens when the robot is then taken away and whether we see any sustained outcomes. So this is probably the largest scale robot deployment we've ever had. This is a large amount of technology in each of these systems. And what makes it particularly nerve-wracking for me is that when we drop the robot off on day 0 or day 1, we know that all the robots are identical out of the box, but we also know that by the very next day, that robot has started to adapt to that child and has started to change the way that it acts and what it does. And by day 30, that robot is different from every other robot that we have deployed. We don't have the final results on this. As I said, we're still midway, but just to give you a bit of a preview, the robots have been, we've been able to run these 30-day sessions, and we have seen a lot of the families who are extremely pleased with the process. They're very unhappy on day 30 when we take the robots away. But just to give you a sampling of what kinds of things we've been able to get, this is one of our moms who on day 30 wanted to tell us this about the experience.
He is so excited to spend his half an hour helping the robot find his way home, and he will come on and I will set it up for him, turn on the robot, and he is engaged immediately. Having the ability to have this robot and to do a half an hour therapy with him that was really specific to what he needs to focus on was just, it seemed like a great opportunity for him, and it's really been just, he's been engaged and intrigued, and sometimes the therapies they get a little exhausting and he's not excited, and this one wasn't like that. He was ready to play at 7:30 in the morning. That we went to the playground one day, and I noticed immediately there was a group of children playing in the sand, and he walked up to them and said, "Hi, what are you doing?" And I don't think he would have done that a month ago. Actually, with the robot, he's engaged, he's intrigued, and so the excitement is there, and he's doing it and he's practicing it, and to see that as his mom is fantastic, that it's in there and we can just keep practicing this with that engagement, that it's getting stronger and it's carrying over to other parts of his life, that things that might not be as engaging, but he'll still practice them. Really watching the skills that were being worked on each day, really it exceeded my expectations.
So I will pause there. So there's lots more that we can talk about, but I want to make sure that I leave enough time for questions here. I want to thank the large number of people who have been involved in this project, actually these many projects over the years, especially to the families who've welcomed us into their homes, and especially to our sponsors who've made this possible. So let me stop there, and I'll turn that over to our moderator for some questions.
Okay, thanks so much, Brian. My name is Katie. I'm the news editor at Spectrum, and I have a few questions. The first one is there any research on robots and teaching idioms to people with autism? I know that there was at least one group who was very interested in that. It was a group based in Switzerland. I know they started a project on that, but I don't know that it was ever published. I've never seen a result on it. It's definitely one of the things that we're especially interested in for young adults, but I don't know that there's anything published in that domain just yet. Okay, and how about teaching job skills to people with autism?
Yeah. So there's a lot of excitement about not only being able to teach particular skills, but also to work collaboratively on skills. And this is part of a much larger umbrella in robotics that's called human-robot collaboration. This is something that many people are interested outside of the autism domain, because they're looking at this as a way for changing the way that we think about factory automation. So if you think about robots in a factory right now, you think about something like an auto assembly line, where there's a conveyor belt, and it brings cars along that conveyor belt, and it brings it from one robot to the next robot to the next robot, and there's no humans in that process whatsoever. That's a mechanism that works if you're a very large company and you can devote an entire production plant for one product. But it doesn't work if you're a local bakery or you're a tailor and you're trying to compete within just a small regional market, but with these very large, very low price point, larger corporations. And so many people in robotics are thinking about ways in which they can bring robots and people together to work on tasks within the same workspace, and how to do that. And that requires a lot of intelligence on the robot's part. The kinds of skills that you need the robot to do there are very complex, and people are just starting to think about that. But I think an important corollary to that will be trying to teach more complex cognitive skills and job skills to people. And the reason I think that there's that relationship is that what you're really talking about is being able to understand the model that someone has of a task. if it's something as simple as I have to teach you, a sequence, do A, then B, then C, that's usually pretty easy, and that's usually something that we don't have a lot of difficulty with. The problems we run into are when you have to do, usually you do A, then B, then C, but sometimes you have to do A, then C, then B, and knowing when you have to switch those two, that's where things get to be really complex. And that's the kind of skill training that's the point in skill training where most of the automated systems just fail. So it's not something that we've got. It's not something that we've got a lot of effort developed in right now, but it is one of the near future things that I think you'll see a lot of work in soon.
Okay, thanks. Another question: how do you think the transfer of skills is happening in your research? What factors might play a role there?
Yeah. So one of the things is that we're really, there's two kinds of transfer here, and I'm going to differentiate between the two. One of the questions we usually get asked is, how do you take a skill that somebody learns with a robot and transfer it to a person? And that's the kind of transfer that I think is not actually happening here, because we're always focused on how the child or how the individual is interacting with another person. And those are the skills that we focus on. So there really isn't necessarily any transfer that's going between interaction with the robot and interaction with a person, because all of our designs are based around human-to-human encounters. Now there's the more general question of transfer of how do you go from the things that you're learning in this particular setting with the robot there helping out and then using it out in your daily lives. And that's one of the things that we're really trying to measure with this month-long deployment. And so we've been asking the parents to keep pretty careful journal entries about the skills that they see the child taking from the robot and using outside in other areas. And we've got a few good anecdotes of this happening. It's still, a month is still a very short amount of time in terms of, really looking at learning over a grand scale. But we think that there are some things that are happening there. And more importantly, we're learning ways in which we can better design these interactions so as to encourage transfer and generalization later on.
Okay. And then a couple more questions. The first is, what is the current state of commercially available robots being marketed as means of interventions to people with autism?
Okay. So this is a great question. There have been, we've been doing this clinically for about 17 years. In the first 10 years, we were extremely closed door. We didn't do any external talks. We didn't speak to the media. We used to, keep this very quiet, in part because we were very afraid that people were going to try to commercialize this too early and in ways that weren't really going to help people. And in fact, this, we just saw some signs of this. There's I won't name company names, but there was a company that 5 years ago started marketing a robot as and I'm going to quote here, and I think this is terrible, but I'm going to quote them, a solution for autism. And it made my skin crawl to see that. Robots are not in any way a cure for autism, or there's no clinical evidence at this point that they show even long-term or mid-term learning gains that transfer. And so any of these things that are happening are very premature. And you will see a lot of these claims out there in marketing materials that this shows real benefit. So that, I think, if the question is, can you buy something right now that is going to be helpful, the answer is probably no. There are a number of startups that are out there right now that have, as part of the founding board for those new companies, people who have done this in the clinical world in a very responsible way, and they are starting to produce commercial products. I can think of two of them right now. Again, I won't name names publicly. I consider that an endorsement, and I'm not making that statement. But I think in the next 2 years, you'll start to see products out there that have really well-designed protocols. They may or may not be helpful. They're going to be very carefully marketed, and we don't have proof that these things are useful, but everything that we have at this point points to at least the idea that they're not causing any harm. So, the first few years it'll be, an unproven technique, but we're hoping to collect more and more data and actually see whether there is, a real clinical utility to these things. But there are definitely companies out there right now that are well poised to be able to bring technology to market at a reasonable price.
Okay, and maybe one or maybe two more questions. Are there subtypes of children with autism that would benefit more from the use of robotics in their treatment?
Yeah. So we often get asked that question. A lot of our work focused on a cohort of kids who were roughly 6 to 12, relatively high functioning. We have done a lot of experimental work with kids at different ages. We haven't done a lot of work with folks above 16 or so. They don't tend to come through the clinics that we work with. But we have worked with kids who are who have more challenges than the kids you've seen in the videos. If anything, I would say one of the really interesting pieces that we have is that many of the robot-based technology interventions have more of an impact on reducing stimming behavior and other antisocial behavior than just about any other intervention that we've seen. I didn't talk about that result today, but that's one of the things that we do see. If anything, I think kids who are probably on the lower functioning end of the spectrum may have more to gain, and this may be a better match for them.
Okay. We'll leave it there for questions. A complete replay of the presentation will be available on the Spectrum News site in a couple of days. This webinar is part of an ongoing series, so please check our site for upcoming talks to be announced soon and video archives of previous webinars. The next webinar will be a journal club featuring 2 papers investigating therapies for Rett syndrome on the 11th of December. Thanks again so much to Professor Scassellati, and thank you all for tuning in.